Hello, today we're going to be doing MCMC in RevBayes, and we are going to be writing some functions by hand to perform this Markov chain Monte Carlo analyses. And we are going to be using it to look at our coin flipping model that we introduced in the last video. So our learning objectives for this video. First, we just want to give a brief overview of Markov chain Monte Carlo. I'm not going to be going too in depth to the math or some of the nuance for how this works. I just am going to be giving a sort of big picture, sort of high level idea of Markov chain Monte Carlo. And then, but if you are interested in MCMC, I will have some resources linked in the description of this video. Now, next, we want to be able to write an MCMC algorithm, and we will be doing that in RevBayes. And then lastly, I just want you to appreciate that the MCMC machinery is already implemented in RevBayes, so we don't actually have to go through this process of writing an MCMC algorithm for what we want. So first, MCMC, I like to think of it as a robot that moves around parameter space in a sort of stochastic manner. And the kind of special thing about this robot is that the robot tends to spend more time in places with high posterior density. So imagine if this was our parameter space, if we were looking in 2 dimensions here in parameter space, then this landscape here represents our posterior density, where this sort of red peak here is an area of high posterior density. And then as we move down into our yellows, greens, and then blue, we are getting lower and lower in posterior density. So our little robot will be kind of meandering all throughout this parameter space, but it will be spending, assuming we ran our MCMC long enough, it should be spending most of its time up here, and then sometime in this yellow and green area, not very much in this blue. And this is how we estimate our posterior distribution, is we kind of look at where this robot's been and we ask kind of where it's hanging out most of the time. So we can visualize kind of what our little robot is doing if we take a sort of bird's eye perspective or a top-down view on this. If we are looking directly down on this landscape, it might look like this. And so this circle here might represent the sort of red peak of our landscape, whereas between these 2 circles is that yellow and green area with sort of middling posterior density. And then anything outside of those circles is that sort of blue area of very low posterior density. And then this blue circle will represent our little robot, and it should, if we run it for long enough, it should, sort of estimate this sort of peak here, or this sort of landscape. So we can see, we'll run it for 3,000 or maybe more. We'll go 4,000. So we ran it for 4,000 generations, and we can see our little robot. It tended to hang out, the most in this area right here, with a sort of where the high posterior density is. And then, it definitely didn't hang out as much around this circle. And then we can see it barely spent any time, relatively speaking, outside both of those circles. So this is kind of what our MCMC is doing. And one more thing I want to show is kind of how our MCMC is moving throughout this sort of space. So what we can see here is that our MCMC, it starts off right here and it moves. And anytime it moves and it accepts a move, it's represented with a blue line. And anytime that it proposes a move but rejects it, it's represented with a purple line. So for example, when our MCMC was right here, it proposed a move way out here, but it rejected it. And then, later I can't tell which direction it's going. I think it's this way, but then later it might have proposed this move and it accepted it. And so what our robot's doing is it's kind of moving all throughout this parameter space, kind of meandering. And we should see it, as we do enough moves, that these dots sort of start to resemble our posterior distribution. So that's how we can sort of think about this. And to do this in RevBayes for our coin flipping example, what we're going to do is, first off, we're going to want to start with a few functions this first one will just be our likelihood function. And this will just be the likelihood of, the probability of heads given our data. There we go. And so for this likelihood function, one thing to note is that this first line right here, if we are ever less than 0, if p is ever less than 0, or p is greater than 1, we want to return 0. And this should make sense because the probability of heads should only be between 0 and 1. It should never be outside of that. So anything outside of that should have a likelihood of 0. And then otherwise, if it's inside of it, we just return the likelihood from the binomial, given our data, which is x. And then the other function we need is we need a prior function. And this prior, this is just the prior of p from our beta distribution with parameters alpha and beta. And again, we can only have values between 0 and 1. So if it's outside of it, we want to return 0. And then the last thing we really need is a way of proposing new moves. And the move we're going to do is we're going to do a slide move. And what this move is doing is kind of right here, it kind of sums up what it does, is to propose a new value of p, we start off with the current value of p, and then we make a draw from a uniform distribution, and where that uniform distribution ranges from negative delta to positive delta, where delta is some value that we pick. So delta really, it controls kind of the size of this uniform distribution. And so what we do is we make a draw, and then we just add that to the current value of p, and then we decide whether it gets accepted or not. And if we accept the proposal, all we do is we say that p is now equal to our proposed value, and if we reject it, we don't do anything. So that is our move for our MCMC, and now all we need to do is initialize our MCMC with some values. So first we want our values of alpha to be 10 and beta to be 10. And then to start things off, we just make some draw from a beta distribution. We'll make one draw with parameters alpha and beta. And then also for our data, we don't have x right now. For our data, we're going to cheat a little bit, and we're just going to say that x is the sum of all of our data, because dealing with multiple data points, it gets kind of messy for those functions. So we're just going to simplify it. And then our n in this case will just be data.size multiplied by 10, because we did 10 coin flips for each of those data points. So then all we need to do is we can just write our algorithm, and we just do a for loop, but we will start off with some number of reps. Let's say we do 10,000. So then we just do for rep in 1 to 10,000. And then we open up our for loop, and all we do is our slide move, and we will use a delta of 0.1. And then what we're going to do here is we're going to use an if statement, and this is just to print kind of where our MCMC is at. So if rep is rep modulo, we'll go 10 is equal to 0. So all we're saying here is every 10th iteration for our MCMC, we're going to print off what the value of p is in our case. So rep and p. So we're going to print off the value, our current iteration, and then the value of p. And then we just close our for loops, and then we can see it chugging away. And one thing I want you to note is kind of how fast this is moving, and compare it to for the next video, because there's quite a difference in speed, and this definitely is not optimized very much at all. So this is quite a bit slower. but we can see that our MCMC is kind of moving around in parameter space. And we could record this and write it to file, but we won't bother for this video. And so yeah, there we go. There's our MCMC. One thing I would recommend checking out is in the tutorial there are other moves that they propose and that are written, but I just chose to do the slide move. But it's kind of fun to think about, which moves might be more efficient or which ones are good for our particular case. So yeah, thanks. In the next video, we will be using some of the built-in machinery to do the same sort of analysis, and we can kind of compare things and look at our runs for that. So thanks.